Okay, so we are looking now at section 6.4, arc length, and it's a very important topic. It comes up in multivariable calculus as well. How many have to take Math 280 for their, okay, IB does, Helen, Masume, OPME, and so this arc, and Susanna, this arc length is important. Like, you know, one application of arc length is, for instance, the length of a DNA. You know, the length of your DNA. It's in terms of angstroms, and you know, a helical DNA is pretty long. But of course, that's three-dimensional, so you would need to adapt the arc length formula for three-dimensional space curves. But that's not hard to do. You know, so it's good you're learning arc length here in calculus 2, and you'll see it again. So in this problem, you want to find, we're going to find expressions for the length of the arc of the curve. Now this curve is given as y to the 3/2 power equals x from 0, 0 to 1, 1. Okay, so let's see here. Now, if we wanted to plot this in Desmos, here's what we would need to do. Desmos likes its parametric equations in terms of t. Okay, so you could let y equal t, and then x would equal t to the 3/2 power. And so in Desmos, if we wanted to graph this arc, okay, which and what is this? This is just x is a function of y. That's some kind of a function. X is a function of y, so y is the dependent variable here, but you know, we're going to graph that this curve from 0, 0 to 1, 1, and the way we do that is for Desmos we need to work with t as a parameter. So we're going to let y equals t, then x will equal t to the 3/2. So what we'll type in Desmos is t to the 3/2 and t, because t to the 3/2 is x and t is equal to y. So I'm going to go into Desmos here. Okay, I'm going to go into Desmos, and I'm actually going to, and you also please go into Desmos. By the way, for this problem, what would t go from? If we're going from the origin to the point 1, 1, that's right. Good. That's right, Jonathan. T would go from 0 to 1. Okay, so in Desmos we go, and I'm going to type it out here a little bit before, you know, before I bring it up here. It's let's see, t to the 3/2. So t to the 3/2. Yep, got it. And t, nope. I'm going to show it to you here. Okay, let me bring it here in Desmos. Let me bring it up here. That's right. I'm bringing it up now. I wanted to type it in first, Jonathan, before I brought up the Desmos. So let me bring it up now. Okay, is Desmos showing okay, everybody? Give me a thumbs up if it's okay. Good. Thank you, Clea, and thank you, IB and Avery. So okay, so there is our curve, and you can see the curve. There's a lot of wasted space here, so I can move that, you know, curve a little bit here, and there it is. There it is. So that represents the function x equals y to the 3/2 power. And in this case, we're interested in finding an expression for the length of the arc. Once we have an expression, we can evaluate it. But are there any questions so far? Okay, okay. So let's go back to the handout here, or to the example. Here we are. So let me ask you, for graphing this curve in Desmos, we needed to have t as the parameter. But could we let, being that x equals y to the 3/2, could we let y be our parameter? I mean, is there any, could we let y be the parameter instead of t? The answer, of course, would be, well, the answer will be yes. Let me show you why. Let me just go to the solution here. Mark, we don't want to square both sides. We want to leave, because when you square both sides, I do see what you're meaning. Oh, I see what you're saying. I guess we could square both sides of the equation, but I'm going to not do that. I'm going to just choose to leave that as is. I mean, in other words, what I'm trying to say is parametric equations are not unique. You can get multiple parametric equations that'll graph out the same curve. So what Mark's saying is, if we squared both sides of that equation, y to the 3/2 equals x, we would get y to the third equals x squared, and that will trace out the same curve. You're correct, Mark. You are correct. But for what we want to do, we can just work with the x equals y to the 3/2 power. But that's a good insight. Good insight. So there are two methods here we can use. One is we can let y be the parameter. We can let y be the parameter. And if we did, then y would be between 0 and 1. Y would be between 0 and 1. And of course, the formula you're used to using is the arc length formula, where t is the parameter. But if we decide that y is going to be our parameter, we can replace everywhere we see a dt, we can replace that with a dy. Because t's not where, if we let y be the parameter, then instead of dt, you'll have dy. It's a different parameter, but it goes in the same place, in the formula. And so what happens when we do that is you have there dx dy squared, but then here you have dy squared. Well, that's just 1 squared. That's just 1 squared. And so the formula, the arc length formula, collapses. This is an, let me use the stylus here. The arc length formula here use my little eraser. Mouse seems to work better for erasing. I don't know why, but okay. So the arc length formula is now collapses into this formula. And this is actually formula 3 in your section 6 in the textbook, section 6.4, formula 3. There's another formula for when you're treating x as the parameter. But this would certainly be okay. Are there any questions on that? You're adapting the formula to the curve that you're using. The first example we did, the curve was expressed as parametric equations with regards where the parameter was t. And so I, used that form of the arc length. But if y is the parameter, you can use this form of the arc length. Now, what would that look like in terms of our problem? Well, I'll go to the next page if everybody's okay. Okay, are there any questions? Okay. Well, so dx dy is the derivative of y to the 3/2 power. That's just 3/2 times y to the half power. And so the arc length is going to be equal to the integral from 0 to 1 of the square root of 3/2 y to the half power squared plus 1. Because this is just dx dy. Are there any questions on that in general? You can wait. Yes.
I'm not
Yeah.
sure how you got dx dy equals what you wrote.
Well,
Where did y to the power of 3/2 come from?
So our function, of course, is y to the 3/2 power equals x. And so what I'm doing is I'm saying, all right, I'm going to let x equal y to the 3/2 power, and y is just going to be y. These are my parametric equations right here.
Oh, you're just, oh, okay, I see. Never mind. All right, thank you.
Okay, you're welcome. Are there any other good questions? Okay, well now this here, incidentally, if you were to work this out, you'd have 9/4 y plus 1 under that square root symbol, and you could get the antiderivative. You would need a substitution, let u equals 9/4 y plus 1, but it would work out. Now the other method is to say, well, I like t as my parameter. I want t to be my parameter. Okay, if you do that, you could say, well, let y equal t. The reason I'm saying let y equals t is because in regards to our curve, where x equals y to the 3/2 power, it's natural to say that y is the independent variable and x is the dependent variable. Well, I'm just going to let y be my parameter. I'm going to let y equals t. Okay. And so then the curve becomes x equals t to the 3/2. And so, it's easier to let y equals t and then have x equals t to the 3/2 than do it the other way. And so now the arc length, we use that standard formula where t is your parameter. That's formula 1 in section 6.4. And you see, you're going to get you know, you're going to get an integral from 0 to 1 of the square root of 9/4 t plus 1 squared. 1 squared is just 1, right? So you get the same integrand, only your variable is t instead of y. Okay, are there any questions on that? How many like the first method where you let y be the parameter? Does anybody prefer the first method? Okay, Yonatan likes that. Hold on here. Clea and Masume, all right, good. Who likes the second method where you let t be the parameter? Usually one person likes the second method, but all right, Niat likes that. All right, good, good. Okay, well, you know, sometimes students think, well, you know, I have this integral using method 1, and then my friend has an integral using method 2. The two integrals, you know, one integrals with respect to y, the other integrals with respect to the, well, one integrals with respect to a parameter y, the other integrals with respect to a parameter t. Are those two integrals the same? And the answer is yes. I'll show you that. So, well, I'm not showing, yeah, hold on. Go back a slide. Yeah, go back to the previous slide. I can do that, Avery. Everybody's good here? Okay, here we go. This is what you're looking at, Avery. Okay, great. Okay, well, you see, whether we have used the parameter y or the parameter t, method 1 or method 2, the integrals are going to be the same. So, you know, here was the integral for, well, hold on. Here was the integral for the first method, where y is the parameter. And here's the integral for the second method, where t is the parameter. And you can see that, yes, the variables are different, but you're going to get the same result, whether you know, the definite integral is going to give you the same value. See that? It's kind of, does it help to see them side by side to convince you that both integrals you get the same answer? Okay, wonderful. Thank you, Yonatan. Excellent. Are there any questions? Who's feeling good with arc length? Who's feeling okay with it? Okay, wonderful. Susanna, Mark, Niat are feeling good, and that's great. Gabriel, wonderful, wonderful. There's more we can do with arc length, but section 6.4, we'll talk a little more about that on in Monday's class, along with some new material. But this is good, I think, for today. All right, let me stop the recording.